All right. Well, hello everyone, and welcome to our presentation today on MPC 609, durable bridges using glass fiber reinforced polymer and hybrid reinforced concrete columns, hosted by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University. TLN is a dynamic partnership with the four state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Center for Transformative Infrastructure Preservation and Sustainability, known as CTIPS, which is formerly known as MPC. This partnership allows us to deliver technical transfer, best practices, training, and research to the transportation industry. For more information, visit our website at translearning.org or ctips.org. Our speaker today is Dr. Chris Panelides. He's been with the Department of Civil and Environmental Engineering at the University of Utah since 1991, where he is currently a professor and associate chair. He received his BE in civil engineering from the American University in Beirut in 1980, his MSc from the University of Missouri-Rolla in 1983, and his PhD from the University of Missouri-Rolla in 1987. He was a design structural engineer in 1980 with Dar al-Handashah Consultants from 1981 to 82. He was a construction engineer with Odin and Odostromaton SA. With that, Chris, I'm going to go ahead and mute myself and let you take over from here.
Thank you, Chris. Good morning, everyone. I hope where you are is cooler than where I am here in Utah. So today I will talk to you about durable bridges using glass fiber reinforced polymer and hybrid reinforced concrete columns. So first, let me put here an outline. And in my outline, I will try to cover the introduction, why we're doing this research, the proposed research, what are the components of the research, which includes an experimental and a computational component, some pull-out tests that were done because we're using fiberglass bars and spirals. The fiberglass spirals, we used them in the past, but to use fiberglass bars to reinforce a column which is actually precast is something new. So we felt like we needed to do this pull-out test. And then we did two components of an experimental study. The first part was using grouted ducts. We constructed two columns, one which was reinforced only with steel bars, longitudinal steel bars. The other was reinforced with what we call a hybrid. Hybrid meaning some of the bars were steel and some of the bars were fiberglass. For both of these columns, the lateral confinement reinforcement was actually fiberglass. And then the next stage is the post-tension column experiments. This is very similar to the previous two columns. We constructed two additional columns. But these ones had all, in addition to the previous reinforcement, which was in the grouted ducts, they had post-tensioning bars. The post-tensioning, of course, is used to minimize the residual displacements that occur in an earthquake. And the residual displacement is important for the serviceability of a bridge after an earthquake. And as expected, we did observe that the residual displacements of these post-tension columns were significantly reduced. And finally, in this presentation, I will present a computational study which involved both the non-post-tension column experiments and the post-tension column experiments. And I will close with some conclusions. So, introduction. In the last few years, probably 20 years, people are used to the word accelerated bridge construction. Typically, up to recently, bridges are constructed, bridge structures are constructed using monolithic construction, which involves a long time periods of constructing footings, columns, and cap beams, and then laying down the girders and the deck. So in recent years, and arising from construction efficiency and less construction time, people propose accelerated bridge construction. In addition to the quick construction time, we observe that there is superior quality of the prefabricated components because these can be made in a precast yard In addition to that, we have minimal interruption to traffic during construction, especially in densely populated areas. So in the last few years, you can see in these pictures, people have started constructing, and also in Utah, but in other parts of the country, substructures or bridges using accelerated bridge construction. So the idea is all our experiments were focused on this construction method, accelerated bridge construction. So one of the issues when you do this, in Texas, for example, they don't have a problem because they don't have earthquakes. But if you have earthquakes, the main issue then becomes how do you construct the connections? So the connections can be done different ways. You can have, as you see here, socket connections where you embed the member into the footing and then you pour grout around it. Or you can have the other option, bar coupler connections, for example, with splice sleeves or with clamping screws, threaded sleeves, mating sleeves, and on. There are many different methods to do this. And the last few years, we were involved as well in investigating how well do these connections perform in seismic conditions. For example, we did try grouted duct connections, and we showed that they can, under the right conditions and with the right construction methods, here you can see a coupler and a grouted duct, or you can have pocket connections. These connections can actually perform as well as monolithic connections. So what is the next point to investigate it? So an NCHRP report came out which described the socket connections. They have excellent performance, but slightly difficult to implement. Pocket connections are constructible. Bar couplers are a little bit difficult to implement, but grouted duct connections have good performance and good constructability. So we picked grouted duct connections. Material is available, it's popular. It doesn't depend on a specific manufacturer. We have very good tolerance for assembly because we can pick the duct diameter to vary on our own. Development of grout, we actually developed our own grout, high-strength grout, and that does not depend on a duct manufacturer or the grout manufacturer, and economical. So it must be cost efficient to produce and transport. So we're using a grouted duct connection, using galvanized steel ducts embedded into footing with reinforcing dowels of another member, in this case the column, inserted into the footing. The finishing work, we fill it with high-strength grout. We developed ourselves, as I mentioned, to finish the joint. So the force transferring mechanism, the force from the rebar is transferred into the grout to the outside of the duct. So in this case, we used a column to footing connection, but it can be used for many other places and also as a splice. It can be used, for example, pile to pile cap, spread footing or pile cap to column to cap beam, and splice between column or cap beam segments. So this has a promising and good constructability connection, and that's why we used it ourselves. So here you can see how the columns were typically constructed. They're constructed with 6 grouted ducts, 2 inches diameter. And you can see that in this case, we're using all steel column, but as I mentioned earlier, we also used a hybrid, which means some of the bars were steel and some of the bars were fiberglass. So what is fiberglass? It's a fiber-reinforced polymer. It's a composite material system made of fibers, which provide the strength and the stiffness. In this case, it's glass. And the matrix, which protects and transfers the load. So it makes a composite member, like you see here. And it has a superior quality, which has a very good property. So we use fiberglass rebars and spirals, as you can see in the picture below, to provide significant merits over traditional steel. The main idea here is, why are we calling these durable bridges? Because if you have fiberglass bars At least some of the bars are fiberglass. And all of the spirals are fiberglass. They are non-corrosive. So while we're examining the viability of these connections to earthquake excitation, we're also saying that these are non-corrosive. The fiberglass has a high strength to weight ratio and has an ability to form in any shape, although here the only shape we're interested in is longitudinal for the longitudinal bars and the spiral. So what are the properties of these materials? So we use number 6 glass fiber reinforced bar, as you can see here in green, which actually has a pretty good tensile capacity. It has 100 KSI ultimate strength and a 1.5% ultimate strain. And as you can see from this graph, is an elastic material. It doesn't yield. On the other hand, grade 60 steel was used, which has a yield strength of about 0.2% and a yield stress a little more than 60 KSI. This is an idealized graph, but it can show you that there are, of course, advantages to using steel. It yields early, and its ultimate strain capacity is more than 3%, way more than that. Whereas, of course, fiberglass is kind of has a low modulus, but on the other hand, it has a higher strength of about 100 KSI, as I said. So we try to combine these two materials to make a good connection. So the first two tests, as I mentioned, were not post-tension, but the last two were post-tension. So here you can see on the right a picture of a post-tensioning system. In this case, we use high-strength threaded bars. Other people have also used the strands. And these are unbonded post-tensioning bars that we use. So what happens is the strain increases in the post-tensioning bar and is distributed over the whole length, which allows these bars to remain elastic at large lateral displacements. So it provides a restoring force to the basic system. And of course, the reason we're doing that, as I mentioned earlier, is to minimize the residual displacement of the bridge. And if that's the case, then the bridge is reusable right away, right after the earthquake. So the research gaps here is that there is no information available for the development of these fiberglass bars in grouted ducts. Only a few references on the seismic performance of precast fiberglass reinforced columns is available. And there's no information actually on seismic performance of combined fiberglass and steel reinforced columns. No information on the seismic performance of these hybrid columns with post-tensioning to see if they really self-center and if they bring the columns back to zero. And no information actually on this performance of a very specific type of hybrid columns where we use 2 layers of longitudinal bars, as we'll show in the next slide, and which require a double layer of fiberglass spiral. So an inner layer and an outer layer of fiberglass spiral. And then finally, of course, there is not much information on modeling analysis of these 4 specimens that I talked about. Before we started the research, though, we had to make sure that we are proposing a bridge approach with ABC, accelerated bridge construction, for a corrosion-resisting bridge with self-centering capability to substantially reduce or eliminate permanent residual displacement. And in the ducts, we use an ultra-high performance graft. So for the non-post-tensioning columns, these 2 specimens were built and investigated to see how the hybrid reinforced system seismic performance works using conventional steel and fiberglass longitudinal bars. And then for the post-tension group, we have 2 more columns which have post-tensioning with high-strength threaded steel bars, as I mentioned, to improve the self-centering. So let me get into then what the non-post-tension columns look like. It's an octagonal shape, which is chosen because actually UDOT and other DOTs use for ease of transportation and facilitating handling of such a column. The diameter here of the octagonal shape is 406 millimeters. And as you can see, there are 2 layers of bars. So the red dots indicate the steel bars, which are on the outside, and the green indicates fiberglass. So as you can see, there are M19 fiberglass bars. These are on the inside. And there are also M19 steel bars. These are the steel bars on the inside, on the outside, and the green bars are on the inside, sorry. Regardless though, you can see that there are 2 circles. These are the spirals, and those are M13 fiberglass spirals at 50 millimeters. So the first cross section is shown in figure C, and figure C shows you then the hybrid. You can see the steel is the red, and the green is the fiberglass. And then the one with the 2 red dots means that both of the bars, the longitudinal bars, are made out of steel. So the first one here, figure C, is the hybrid, and the second one down here, figure C, is the all steel column. These columns are embedded into the ducts, as you can see here in the footing. And in addition, they are actually debonded. We use duct tape, very high tech material, to debond roughly 152 millimeters of these bars inside the ducts. And this debonding allows the development of very high strains. So this is good for getting a ductile column in a seismic setting like this. So here, this graph shows you the post-tension columns. Those are the next 2 specimens, and you can see here the 2 post-tensioning bars. These bars are 25 millimeter high strength steel bars. They're Williams bars is what they are called, and they are inside a 2-inch PVC pipe. I will show you the pipe. In addition, the debonded length here with the duct tape is longer. It's 304 millimeters. So in addition to debonding in the footing, there is also debonding in the column. The rest is the same. And you can see the post-tensioning bars are located near the center of the column, inside the very, very close to the center of the circle. So before we started building these 4 specimens, we realized there was no information on what is the pull-out capacity of a 19 millimeter or number 6 bar in a grouted duct. So we constructed some specimens for pull-out testing, so we could make sure that when we embed them inside the grout, we will actually have a good performance. So we constructed some cylinders made of concrete that you can see here of varying lengths and varying embedment depths. And we tested them for pull-out strength. We used the same type of grouted duct that we use in the large experiments. And this is where we developed the ultra-high performance grout. And you can see this grout developed 10,600 PSI in 28 days and higher strength than that. So the main components were silica, sand, cement, and water. So as we predicted, there was a point where the bar pulled out if the embedment length was very short. And then we found out there was bar fracture, which is the desirable mode of failure. And we determined that 14 bar diameters were actually more or less an acceptable length. And we use a much higher embedment, of course, in our experiments than this. Much more research, of course, is required on this front, and these were just some preliminary tests, but we knew our columns would work. So again, going back now to the non-post-tension tests, I'm showing again the cross-section of the column and the reminder that there was a little bit of debonding inside the footing. roughly 6 inches. But you can see here the 12 bars that are used. In this case, in the hybrid case, 6 are steel and 6 are fiberglass. And in the all steel case, all 12 bars are, of course, steel. So this shows you pictures of the construction. This is the all steel column, and you can see the double fiberglass spiral. We're calling this the all steel column. And this is the hybrid column with 6 steel longitudinal bars and 6 fiberglass bars. And again, we have the double fiberglass spiral. And this picture shows you the 6 grouted ducts which are in the footing. So in order to study the seismic performance, we actually built on the strong floor, we attached the footing, and then we lowered the column inside the ducts. We grouted the ducts, and after 28 days, we were able to apply the lateral load using a servo control hydraulic actuator. It has a capacity of 800 kilonewton and an overall stroke of 610 millimeters. We also applied an axial load through these threaded rods. The axial load was typical for columns of this nature, about 6% of the capacity, axial capacity of the column. And this is the loading protocol that we implemented with increasing displacements, 2 cycles at each drift ratio, with drift ratios all the way to 10%. And typically we design these types of columns not to exceed a 2% drift ratio. But of course, in a laboratory setting as this one, we want to see the ultimate performance. So we try to go all the way to 11%, which was the capacity of our machine. So here you can see on the left the hysteresis performance of the hybrid. Everywhere you see the acronym HYB means that this is the column with 6 steel bars shown here in red and 6 fiberglass bars shown here in green. And of course you can see how we applied the load and pull and push. We started with a push, and you can see that on the left is the performance of the hybrid column in blue, and on the right is the performance of the steel column, which has 12 steel bars, longitudinal bars in red, and we have the acronym STL. So what you can see in this picture is that on the left, on the hybrid column, we have an increased lateral force that increased gradually up to about 9% drift ratio, which is a very large drift ratio. And on the right, in red, you can see that the steel column performed well, maybe even better, which has a very high stiffness in the beginning. You can see the slope here, up to 3% drift ratio. And at that point, as is typical for these steel columns, it achieved a very good plateau. This may seem to be a common conclusion, but the reality is that there are new things here where, for example, we're using fiberglass spirals and 2 layers of it. So this is really a new result. It hasn't been shown in the literature. But I would say that if we compare the performance of these two, which is shown here, again, the hybrid is in blue and the red is in steel, you can see that the hybrid achieved good capacity, 120 kilonewton at 9% drift ratio. The steel column achieved a little higher, 130 kilonewton, and that was achieved earlier at 6% drift ratio. So there is less than 10% difference in capacity. The ductility of the steel column was a little bit higher, 5.5, and the ductility of the hybrid was only 4. But even 4 is a good ductility. And on the right-hand side, you can see the hysteresis envelope, which explains what I just said. So as far as how did failure start, in the hybrid column that you see here, at about 6%, we started seeing 6% drift. We started seeing spalling for the first 250 millimeters of height, the first 10 inches. And this exposed the outer layer of the fiberglass spirals that you can see in this picture. This happened at around 6%, which is still a very large drift. And then at 9%, we saw that a fiberglass longitudinal bar fractured. You can see it here in this picture. This is where it fractured. And then the steel bar, the west extreme steel bar, fractured at 10% drift ratio, and you can see it here. This picture was taken at 11% drift. And then another bar buckled, and of course, a steel bar fractured. So, and then the spiral also fractured on the extreme west side. The failure of the steel column at 6% drift ratio, we saw spalling. This spalling was about a foot, 300 millimeters high at the base. And the cracks progressed until 11% drift when the outer steel bar and 2 turns of the spiral fractured, as you can see here. And this happened at 11%. 11% is an unbelievably large drift ratio. It will never happen during an earthquake, unless the earthquake is really, really very, very strong. So how about the residual displacement? Remember, these columns were non-post-tensioned. So even without post-tensioning, the black line shows you the peak applied displacement, and the white line shows you how much was the residual. So for example, at 10% drift ratio, the residual was about 3 inches, 3.5 inches. So on the left, you see the hybrid, and you can see the hybrid has actually a little better performance than the one on the right, which is the steel. We expected that because the longitudinal bars of the hybrid column are elastic. So when you have something elastic, if it doesn't break, it will come back. It will tend to recenter. So for example, for design, as I mentioned, we're interested at 3% drift. So if we go all the way down to 3% drift, the hybrid had a residual displacement of only 9 millimeters, whereas the steel had a 13 millimeters. So it's a little higher. And then at 6% drift, the residual of the hybrid was 37 millimeters. That's down here. And then the steel had a residual of 65 millimeters, so almost double. Now for reference, most codes consider 1% residual as the limit to being serviceable. So here 1% means 22 millimeters. So if I drew a line at 22 millimeters, you'd see that the hybrid actually performed better than the steel. So the other part here I want to talk about is, well, here actually this first graph on the left explains the difference between the steel, which is the red line, and the hybrid, which is the blue line, regarding their performance. So if I draw a line roughly, let's say at 25 millimeters, a horizontal line, you can see that the steel will exceed that at about 3%, whereas the hybrid can go up to 5% drift and still be okay. And then this graph on the right shows a comparison of the hysteretic energy. Hysteretic energy is the ability of the column to absorb the earthquake input energy, and we determine this by calculating the area of the hysteresis loop. So these two specimens were pretty similar up to the design drift ratio of 3%. And after that, the steel column, the red, dissipates much more energy, of course, as is shown here. So this is the compromise. You can see in these two curves, if you want to dissipate more energy, you can use the all steel column. And if you want to minimize the residual displacement, you should be using the hybrid column. So of course, this now shows you why we also try to do the test with the post-tension columns, because we wanted to investigate how much better can we make this residual displacement, which is already pretty good. One more thing we studied was the curvature profile. The curvature tells you how the curve is, how the column is actually performing during the test. So here in these graphs, you can see we have on the left the hybrid at increasing drift ratio. up to 6%. After 6%, we had to take out the instruments so we didn't damage them. And on the right, you can see the all-steel column. And basically, what you can see is that the all-steel column concentrates all the curvature at the bottom 200 millimeters or so, which is very typical for all-steel columns because this is where the bars yield. And on the left, you can see that the fiberglass bars, they do not yield, which results in a more uniform curvature distribution along the column length. This is also shown by this graph, which demonstrates the strain in the bar. So you can see that we exceeded the yield limit for these bars for the hybrid column. This is for the hybrid column, up to 17 times the yield. And for the fiberglass, we exceeded that up to 1.5 times the ultimate strain, because at that point, of course, we had a fractured bar. And then as far as the fiberglass spiral, we didn't actually reach more than 1/4 of the ultimate strain of the fiberglass, which means our design was efficient and it didn't go higher than that. Of course, backling caused some of the fractures of the spiral. So now I move into the next phase, which is the post-tensioning columns. These were the two tests that we did in addition to the previous two, where everything was the same as far as the longitudinal bars. The hybrid had a combination of 6 steel bars and 6 fiberglass, and the all steel had 12 steel bars. But now the new element is, of course, the addition of the 2 1-inch threaded high-strength steel bars. These bars have a yield strength of about 120 KSI and an ultimate strength of 150 KSI. So they're very strong. The idea is that these bars are unbonded. There is no bonding between them and the concrete. So they are free to elongate. And the idea is that we should design these to remain elastic. So as the column wants to displace laterally, actually these bars are elastic and they come back and they bring the bar back to the original position. So here there is a picture that shows you the 2 columns. And the difference here, of course, is the ducts. These ducts were 2-inch PVC pipes, and they were placed both, of course, in the footing and the columns. But you can see the hybrid is there and the all steel is there. And both of these, as I mentioned, have the double fiberglass spiral. So the test was run very similar to the previous 2 tests that I mentioned about. The only difference was, of course, the presence of the post-tensioning bars. And you can see here we kept an eye on the force level, the post-tensioning force in the bars by these load cells. Each post-tensioning bar was initially post-tensioned to a force of 191 kilonewtons. So this force was deemed to be appropriate for this test, bearing in mind we could reach 10% drift ratio or higher. So this shows the performance then of these 2 columns. You can see on the left, the hybrid column with the 2 post-tensioning bars had a high, gradually reaching a high, the peak force capacity of roughly 150 kilonewton. And that happened at about 10% drift ratio. And on the right, you can see the steel column, which reached a very similar lateral capacity. But this capacity was reached earlier at about 6% drift ratio. And in the end, it achieved a very high plateau, as you can see here, whereas the fiberglass column doesn't have a plateau. Comparing the 2, again, you can see the steel is the red and the blue is the hybrid. We can see that they perform very similarly in this case because of the post-tensioning. And the hybrid reached the peak at 10%, whereas the steel column reached a very high capacity at around 7%. So the difference in lateral capacity was less than 5%. And you can see here in the envelope They perform very similarly, although, as I mentioned, the hybrid kept increasing, whereas the steel reached a plateau. Here we can see the hybrid failure. Now, I forgot to mention that in these post-tension columns, we need to protect the concrete. So in addition to the internal reinforcement, we actually had carbon fiber, 2 sheets, applied at the base of the column. Most people use steel jackets to reinforce the bottom of post-tension columns. But in this case, we wanted to keep the theme of corrosion resistance, so we use carbon fiber. So here you can see the carbon fiber actually held. It held very well for the hybrid column, up to about 6% drift ratio, where at that point, the carbon fiber ruptured or at least cracked. And then at 10%, the carbon wrap fractured. And we can see it ruptured about a 2-inch strip, just came off. But of course, at 11%, we saw that one of the mild steel bars fractured. So 11% is an unbelievably high drift ratio. I need to stress that. And the performance, as you saw up to that point, was excellent. The steel column had a similar fate. We saw the first crack in the carbon fiber at around 3%. At 9%, we saw a fracture, that you can see here on this wrap, which means it worked very well. Again, a couple of inches from the bottom. And you can see on the right that a steel bar actually fractured at around 11% drift ratio on one side of the column, on the west side. And then on the east side, we saw a rupture at 12% drift ratio. So this is a very good performance. How about the residual displacement? Well, the residual displacement was reduced definitely from the previous 2 tests. And you can see it here. On the left is the hybrid column, and on the right is the steel column. A 3% drift, the residual displacement of the hybrid was 6 millimeters, and the residual displacement of the steel was 8 millimeters. At 6% drift ratio, which is again a very high drift ratio, the hybrid was 23 millimeters and the steel was 48 millimeters. So even though both columns reduced their residual displacement, again, the hybrid was 23 millimeters, the steel was 48. So even though both were reduced, the steel still had double the residual drift than the hybrid. Here on the left, you can see the performance comparing the steel, which is the red graph, and the hybrid, which is the blue graph. And you can see at 22 millimeters, which is the 1% that the codes consider reasonable, it's very close. I would say that the hybrid, though, still does better. And on the flip side, when we look at the hysteretic energy, the steel column does better on the hybrid, even in this case where we have the post-tensioning bars. So what happened to the post-tensioning force? I showed you the load cells that were used to measure this force at all time. And you can see that we're starting here in the middle at 0%, and then we're moving. And you can see this typical butterfly shape. As we increase the drift, of course, the force in the post-tensioning bars becomes higher. But the key number is that this red line is the yield limit of the post-tensioning bars. And you can see that in both the hybrid on the left and the steel on the right, we were able to stay below that number. Okay, the hybrid reached about 88% of the yield limit of these bars, and the steel reached about 91%. So both of these performed very well, and they did the job we wanted them to do. The curvature profiles, you can see on the left, the hybrid is uniform as we expected because, of course, the fiberglass bars do not yield. And on the right, predictably, we see the steel has most of the curvature at the bottom of the column, and we know this because that's where the steel yields. And you can see here the strain profiles in the hybrid column. They were smaller, of course, than the profiles for the ones without post-tensioning. And that's because post-tensioning takes a lot of the force. So the steel reached 5 times the yield, but the fiberglass was only 60% of the ultimate. And the spirals, they were much lower. The strain only about 10% of the ultimate. So this completes the experimental part, which shows that we actually did what we are wanting to do. This shows the steel profiles. This was a little higher because we had achieved more energy, so about 6.8 for the steel bars, the outer ones, and the inner 3.2, and the fiberglass about 3%. So now let's go into the numerical procedure. So here, what we want to do is develop a predictive model that's capable of simulating what we saw here in these columns that we tested. We want to account for the difference between mild steel and fiberglass bars. We want to include the bond slip. We want to show the self-centering, of course, because that affects the residual displacement. And there is some impediments here. We want to make sure we are capturing the confinement of the carbon fiber wraps in the case of the post-tensioning. We want to make sure that we capture the failure modes, which is the concrete crashing, the fiberglass bar fracture, and low cycle fatigue failure of the steel bars, which causes their fracture. So we tried to validate the model that was developed for these tests. So we use OpenSeas, which is an open source software. It has a very large versatile library of materials and elements. And they include simple bilinear to complex models, include beam column elements and continuum elements. Everything was done in Python. Then this is more research than design. In order to make sure that we're capturing the performance, we have a flow chart here, which defines the material properties, section properties. It all hinges on the capturing the length of the plastic hinge. Once we capture that correctly, we go in and model the bond slip, find the global response, which should be less than 10%. And then we try to model the bar fracture, the same cycle as the experiment. And then we capture the energy, and if it's below 10%, we say it's good. We validated the model. If not, we go back, we recalculate the plastic hinge, we recalculate the global response, and then we recalculate the fracture of the bar if they don't match. So we use Mander's model to characterize the concrete, both for confined and unconfined concrete. And there is a point where when we have the carbon fiber wrap, we're also confining the cover concrete and the core concrete. The compressive strength of the concrete was low, 55 megapascal, based on the cylinder test that we did. So this shows the curves for unconfined concrete is the black. Blue is the fiberglass concrete, and the fiberglass concrete confinement is based on the model by one of my former students, Shankohar, 2018. And you can find it in the literature. It's a pretty good model, simple model, bilinear. It works pretty well. And then the red one is the carbon fiber model. So using these models, we can capture the confinement properties of the concrete. And then for the steel, we have to be careful to model the slippage of the bars in the ducts, and we use a model by Haber 2013, which produces a pseudo-reinforcing bar like you see here. This is used to model the bars in the concrete. Low cycle fatigue is also modeled with the Coffey-Manson model, and we use the reinforcing steel material in OpenSeas, which is capable of doing this. The fiberglass bar model, that was more challenging because there is no such model. We used some of the information from our pull-out test, and we came up with this pseudo GFRP bar model, which captures both the tension and the compression capacity. We use a uniaxial material for the PT bars, steel 4, and we use co-rotational truss element to model the post-tensioning bars with steel 4 material properties. This considers both nonlinear geometry of the material, which happens during bending. So this shows you the stress strain curve for the post-tensioning bar. There is a defined post-tensioning bar yield limit, although this is not well defined, but we use something like this, and then the fracture, which of course we never got to fracture. So this is the layout of the proposed model. The column length is segmented into two parts. The first region is in the plastic hinge length and utilizes the modified modulus of elasticity of the bar. And then the second segment is the blue one outside the plastic hinge region, which utilizes the original modulus of elasticity of the bar. So we have also core concrete and cover concrete. And then we divide this into 40 divisions circumferentially and 20 divisions radially. Same thing with the cover concrete, 40 circumferential divisions and 5 radial divisions. Then there is the model, of course, for the post-tension columns. And the only difference here is to include the element, the force beam column element for these post-tensioning bars, which is shown here in red. So what is the result? You can see this is for the non-post-tension columns. We are able actually, for the hybrid column on the left and the steel column on the right, we predict successfully the performance within, say, an error of 3%, up to, up to 3% drift, we have an error of 8%. And then the model stops at around 9%, where the GFRP fractures. For the steel column, we're very close. We're within 1% as far as the maximum load. And again, the model breaks down when a bar fractures. As far as the hysteretic energy, you can see we're very close. We're within 5% for the hybrid column on the left and about 10% for the steel column on the right. And how about the post-tensioning columns? This is shown here. The open CIS is in red and the experiment is in black. And you can see on the left for the hybrid column, we're within 12%. For the steel column, we're within, say, 7.5% error. For the hybrid column, we are within 5% error. So this shows that for the energy, we're very close, almost on top of each other. So the model, we feel, has done a good job. The log-R response was based on the drift. It was within fractions, let's say 10%. And we reached the 9% and 11% that we saw in the test. And the bar fracture was predicted in the same drift ratio as the experiment. So we feel confident about this. Post-tensioning force was within 5% of the experiment. And we also saw in the model that none of the post-tensioning bars yielded. Okay, for the hybrid column, there was a gap in the push of the west bars. And this is justified because as we initially progressed damage and concrete spalling above the carbon fiber, we had a lower post-tensioning force in the experiment. But in the steel column, what we saw is that the post-tensioning at the top of the columns caused a little gap in the push cycle. So when I show this curve, you will see that the numerical model was close. On the left, first you can see that the blue and the red is the model, and the green and the black is actually the experiment. So they're very close, except for the pull cycles, the black seems to be a little bit off. This was the experiment. And as I mentioned, it's because there was a little gap, and that justifies that small difference there, where the bars, post-tensioning bars, were digging into the concrete. But overall, both models did not predict yielding, which is exactly what happened. So we feel that this justifies the model. So the beam column element that was used in the numerical model with the plastic hinge, the backlink, and the low cycle fatigue effectively represents the actual behavior. And it predicts the response of the precast columns with grouted ducts, both at the global and local levels. And the confined concrete for steel, GFRP bars and PT bars models, all of this prove their effectiveness in building the models. And the bond slip was modeled, debonding was modeled, and we think that it's effective in doing this. The hybrid was within very good agreement, predicted bar fracture 9%, the steel 11%, and the post-tensioning at 12%, which is pretty much what happened in our experiments. Of course, I have to stress again, these drift ratios exceed the limits where the current seismic design codes recommend. Of course, we did this because as experimenters, we want to know what is the limit. But of course, we know then they perform very well at 3% drift ratio, which is where designers would like to go. So the intentional debonding were good. The post-tensioning was good. The post-tensioning reduces the residual displacement, and the fiberglass bars reduce it even more. And what's good about this is that since we use fiberglass spirals and some of the longitudinal bars were also fiberglass, that means these columns will have much less corrosion than the columns we build today. So in conclusion, I would say that we really did achieve a more durable bridge, a very well-performing seismic bridge bent, and I look forward to seeing this implemented in the future. So I want to thank everybody for their attention.
Thank you, Chris. Certainly appreciate you sharing this information. That's a lot of work that goes into it. So certainly appreciate you taking the time to dive into it, do the studying, testing, and reporting out for our practitioners to hopefully implement and definitely consider. So what questions do you have for Dr. Panelides?
I hope I was clear in my presentation. I try to break it down. It's pretty complex.
I am not a bridge person, and you know, I've worked on one as a construction inspector many years ago.
Okay.
But again, I felt I understood exactly what you were saying, so it's very well presented.
Thank you.
Well, not seeing any questions, thank you for attending today's TLN event. We certainly appreciate your time and attention. We hope that you enjoyed and gained some new knowledge from today's session. Be sure to bookmark our website at translearning.org as well as ctips.org for upcoming presentations and to find research findings such as today's presentation and other research that is out there. With that being said, we hope you have a fantastic week. Be safe and don't forget to be awesome. Thanks, Chris.